Um, it's kind of fun that I'm here at SLAC to talk about this at Amateur Radio Technology Day, because this is sort of what I had in mind, not the talk, but the actual goal for what I was trying to do was to be able to bring it to Amateur Radio Technology Day and show that it works. And why I titled this talk Personal Journey is because it really was a journey for me of sort of doing something I don't usually do. So I like to build hardware a lot for ham radio. I don't usually write software for ham radio. And sometimes I get the notion in my head that I'm going to do it, but then I somehow kind of lose the impetus to continue. But in this case, strangely enough, I didn't. And it's kind of sparked a new level of enthusiasm about writing ham radio software, something I hadn't really considered doing before. And brought back lots of great memories, and also played into my obsessive-compulsive nature about such things. So I'm going to tell you a little bit about how I came to do this, and a little about how it works, and what we might do after this. So the first thing to talk about is what came beforehand. Now, some of you may have heard me talk about this on the repeater on and off, was I kept hearing about this PSK program that ran on Mac. I'm on the Ham Mac mailing list. I don't usually talk there very much, but I just monitor stuff. And I kept seeing these updates come by like every 2 weeks. So I updated to the next revision, this bug fix, that bug's fixed. And I thought, well, I should scope this thing out. So I just decided to try it and stick it on my machine. I usually use Cocoa Modem, which is another program that has its own issues. And it kind of looked like a Linux program, which is, I know some people really like Linux, it's just not my bag. And so it had all these weird UI controls that were not Macintosh-ish, which looked out of place on my machine. And the problem was that it really worked poorly, in my humble opinion. I know some people have had great success with it, but on the Mac it was crashing and not stopping right. It was putting files in places I didn't expect, and there were many bugs. And my inclination, especially since I've started working at Apple, is to immediately inform the person who wrote the program that there's a problem. And so I send them crash reports, I send them spin dumps, and I send them detailed diagnostics about what went wrong and how I did it. I reported that there were actually resources being stuck in my home directory for the program. And I said, this is not the best plan. And this was the response I got. And it wasn't particularly encouraging. Now, I'm going to not say exactly who did this, but I thought, well, to heck with this, I'm not going to use this program anymore. But I kind of got angry about it, and I thought, well, I'll never touch this thing again. But ultimately I did, because I really wanted to play PSK30 on. I was just in the mood for it. And there's this other program called Cocoa Modem, which works quite acceptably, but the problem is, in order to log, it invokes an Apple script which goes off and does nothing, and doesn't tell you it did nothing, so you forget to log things. So you can hook it up, you can make it work, but it just was kind of, okay, not great. So I set up this program, and I ran it here at Amateur Radio Technology Day, and it worked okay, but it was kind of confusing when it came to log a contact. It was not the greatest thing. I was really missing the Mac experience. And the worst part was I was running out of battery power. And that's a real drag. You're out there, you want to make more QSOs, but the poor MacBook over here is out of the schmutz. So I had to stop, and that's no fun at all. But then, of course, it occurs to me, in my backpack is this great thing called an iPad, which is just sitting there, waiting to be used for some cool purpose. It has an audio interface. It's a pretty fast CPU. It has this wonderful screen, and it's big enough to actually do something useful with PSK31. And I knew that people had done this on the iPhone, but I thought, the iPhone screen's kind of small for this task. But being willing to try, I looked out on the App Store and I found a program called iPSK. And the problem with iPSK was that it was kind of a toy. So it can transmit, it can receive, it doesn't have any capability to automate what you send and what you do with it. And it also has a user interface that to me is just hard to work with. Now, ironically, they came out with an iPad version the day of the first QSO. Now, I don't know if anybody's made any QSOs with it, but there you go. But we'll save that for later. There was another program I ran into. I don't know if any of you have ever used multi-mode on the back. That's Chris Smolensky's Black Cat Systems. Multi-mode is okay. It's not great. It kind of gets the job done in a not particularly useful fashion. But the program that he released for the iPad only receives, so no transmitting. That's not very useful for what I want to do. I actually wanted to have QSOs with people. So I realized, of course, while I'm a ham, right? I do this stuff for a living. How hard can this actually be? You know, it's just code, right? Yeah, famous last words. And I had this great long break for Thanksgiving. I had the week off. So I'm thinking, well, maybe I can get this going for the next Amtech day. So I go to Starbucks, which is my favorite place to go, and I start looking around for code. And what I found was another sort of messy thing. I was hoping I could just get some C++ class that implemented a modem. You know, you put samples in one side, and you get characters out the other, and vice versa. So you put characters in, you get samples out. That's what I wanted, really. But and I wanted to be multi-rate, so that it didn't really matter what the sample rate was; it would do the right thing. But sadly, I couldn't find much. And what I did find was nastily sort of intertwined. For those of you who are software engineers, if you can imagine putting UI code in the modem, it's kind of yucky. And the other really painful thing is that a lot of this stuff is under GNU configure. And if you're familiar with the GNU configure thing, it's this big, messy script, and it's really hard to figure out where all the defines and the make files go and all this stuff. And I don't have patience for that. I want it to just work. Okay, so you know, kind of past the point where that's interesting to me, I guess. And none of them were multi-rate, and I wasn't pleased with what I found. So I found some compromise, and the compromise was by a guy named Mo Wheatley, A4JY, and he's one of the original implementers of the PSK31 modem. And what I found was something that he had done fairly early on that was a DLL. And you think a DLL on Apple? But it turned out that the code wasn't too bad in there. It was sort of tear-outable. So there was a few Windows dependencies and things like that. But it still wasn't. It seemed to say it was multi-rate, but it turned out that it wasn't. So the next step was to take a machete to this thing and just chop it to pieces and scoop out the parts that were important to me. There were all of these weird types that seemed superfluous, that needed to be coerced into or typed out to the right things. There was these Windows-specific classes, one that implemented complex numbers that just seemed to have a real part and an imaginary part, and nothing else of interest. So that was easily replicated. They have their own weird string class. And again, there was UI code in this thing. There was these messages to Windows. I don't mean the operating system, I mean the Windows on the screen. So I stubbed all of that stuff out. I finally found where the characters go in and out. And that was really hard. It was just embedded in the middle of something. It said nothing about characters. It was just a post message. So I had to hunt around. And then I just had to beat on it for a long time until it would pass through the compiler. And what I was doing is putting this on the iOS development platform inside Xcode, if you're familiar with that, on the Mac. And it's GCC for the most part, so it understands standard C++ stuff. So I was able to get most of that in there with a bit of hacking and slashing. And then I thought, well, now I'm really close. So it's getting towards the end of the vacation, and now all I have to do is grab some of those samples that I already have some code lying around that grabs audio samples out of the iPad, and all I have to do is feed them to the modem, and it's going to work. But no. Vacation's over, I go back, I can see it's really close, really close, but I'm really busy, and Amtech Day is coming up really fast. And so I'm trying to find every spare hour that I can at home to hack on this thing. And one thing that I find out early on is that the iPad simulator only seems to do 44.1 kilosamples per second. And so I thought, well, I should just turn this multi-rate code onto this higher sample rate, but no, that doesn't work either. It claims, well, like it takes a parameter that says, give me the sample rate, but it really doesn't do much on the inside. It sets a few of the things differently, but mostly wrong. So I knew that it had to be 8,000 samples per second. It really wanted that. And so I wrote a quick and dirty resampler, just on an interpolator style, just averaging samples, and it just utterly failed. It didn't work at all. And where do you go with this? So you play PSK31 to the thing, and you wait for it to break squelch and start receiving characters, and just nothing happens, and you start poking around inside, and all you see are floating point numbers. And you have long lists coming out of the debugger of floating point numbers, and you kind of scratch your head and go, well, these sort of look like sine waves. You can see a certain periodicity up there to the numbers if you look. You can see up here you got like minus 437, minus 480, minus 483. So something's going on, but something's clearly wrong, but you don't know what. So what I decided to do was use an old trick, which is GNU plot. I don't know if you've ever used GNU plot for anything. It's a cool program. It has nothing to do with the GNU project, apparently, but what it does is just plots numbers. It's really good at plotting numbers and plotting functions, and I've used it for years in various tasks. And I thought, well, this can just read this column of numbers, so I'll just print out a column of numbers. And I copy and paste, stick them in a file, and the next thing you know, I have graphs, which is a huge, huge win. So I can finally, maybe, see what's going on, and it saves me from the maze of tiny twisty passages, all the same, full of floating point numbers. So, for a moment, we'll go off and look at what PSK is and how it works. It requires, in order to debug something like this, you have to know how it works so that you can know what you're looking at and figure out how it might be wrong. So let's talk about PSK 31. So PSK is a very basic modulation mode that's based on phase shift keying. And it phase shift keys by taking the phase and inverting it 180 degrees. And it has a symbol rate of 32 milliseconds. It's thus the 32. It's not 32 hertz, it's 32 milliseconds. The actual bandwidth is 1 over 32 milliseconds for about 31.25 hertz times 2, because it's got sidebands. So it's 62-ish hertz wide. So there's two kinds of PSK. We'll only worry about the B kind, which is binary PSK. That's 2 phases for the moment. And each phase shift means that we're going to change a bit from a 1 to a 0 or a 0 to a 1 or something like that. We put the characters in a sort of a compression that is based on the frequency of the characters that are in use as we type English words. And in some cases, if we use QPSK, which is quadrature phased, we use forward error correction in the form of convolution codes. So the goals, I think, I infer from reading the original documents on PSK, that the person who eventually invented it was to have a narrowband mode that fit in the audio pass band of radios. Basically would work with a single sideband transceiver. And would work really well even when the channel noise was pretty high. So the idea is to have a fairly narrow thing, fairly low speed, so we can take advantage of the channel bandwidth and even work in a fairly high noise environment. So what it looks like, this is a very crude drawing of how those phase shifts might look. So you can see that you'd have like a phase transition there and a phase transition there. And this black line is to tell you that there would be many, many cycles in between at the particular phase in question. So you would have a bunch of at this phase, switch to another phase, and then maybe switch again to another phase, and have lots of cycles in between, many, many off there. The problem with this, of course, if you are familiar with signal processing, is that when you make a really sharp transition like that, you get all sorts of harmonics. You've seen this, and even when we're dealing with antennas. If if you have any rectification, you can create all sorts of harmonics, because that creates these very high speed changes in the signal, and you can't have that if you want a narrow bandwidth mode. The other thing to recognize is that you need some phase reference. So you have to run the signal for a while, find where the phases are, and then you'll know if they changed or not. So then we can encode bits with this. And the way that they're encoded in PSK31 is that zeros mean shift phase at each 32 millisecond boundary, and 1 means don't shift. So if we have a string of 1s, we don't make any phase changes. If we have a 0, we make a change. Now, zeros have restrictions on them. We'll come to that in just a moment. So I actually decided to synthesize what an unfiltered BPSK signal would sound like. And hopefully we'll be able to play that in a second here, but this is what the synthesized waveform looked like. And I went at 32 millisecond intervals, and I flipped the phase in an audio sound editor. So I loaded it up with a sine wave, and I just flipped phases every 32 milliseconds with no filtering. Now when we filter it, it looks like this. So each one of these represents a phase transition. You can see that at the phase transition here, the amplitude is near 0. So we don't actually see that rapid change. It looks very, very slow. Now there are other modulation schemes where you can make it not drop in amplitude like that and still express some kind of phase transitions, but this is the way that PSK works. So the envelope ends up being kind of sinusoidal, which gives us very smooth transition. And the signals themselves are sinusoidal, basically. So let's see if we can get the audio here. Sounds pretty bad, huh? Yeah. If you've heard real PSK, it sounds nothing like that. Now, a way that we do...
I'm sorry, I thought there was a melody.
No, that was meant to be there. That shows you what unfiltered PSK sounds like. It sounds like a melody, doesn't it? So how we get rid of all of that high frequency energy is we use a thing called a raised cosine filter, which is based on another thing that's actually called a Hanning window. And a Hanning window is just basically a cosine that where the sort of 0 part is right on the 0 line. And you just have this upper part that's just a cosine going up and down. And it doesn't give you the best filtering characteristics, but it has one really winning property for these kinds of things. And that is that it has a 0 amplitude right at each symbol transition. So right there where it says T, it's hard to see on the screen, but it helps filter out intersymbol interference. So it's not the best low-pass filter, it's not the sharpest one, it's not the flattest passband, but it works really great in this particular domain, so it's often used in signal processing. And it's really simple to implement too. It's just a cosine shifted, just like it says right here. And this signal you see here, we'll be talking about this in a little more detail later, but that's called a sinc function. And a sinc function is sine x over x, and we'll discuss a little later on why we care about that particular function. Now QPSK, that's quadrature PSK. And that's where instead of going 180 degrees, we actually go 90-degree phase shifts. You can see some of the phase shifts up here. It's a reasonable way to look at it. But again, you see the sharp transitions. We have to do the same tricky stuff. But now we get 4 possibilities. So we can encode 2 bits. And that gives us a higher data rate, but at the cost of being more susceptible to noise. So what we do to try and make life better for us in QPSK land is we actually put some redundant information in. So we end up slowing the data rate again by placing some redundant information inside the signal. And that allows us to do some tricky stuff on decoding that gives us a way to factor out many errors and make good guesses about what the real intention was when the signal was sent. Of course, we can't win too much. Shannon's law is always lurking out there trying to get us. So we can't get too much information out of the channel. There are just theoretical limits. And we also get other things like tighter tuning requirements. Some of that is ameliorated by automatic frequency control that's inherent in many of these decoders. They can actually find their center frequency and decode better. But it's It works really well on noisy channels. On clear channels, if anything, it's a little worse. But when you get above a certain noise threshold, it tends to work even better. One of the things we do to try and get the data rate up a bit is we use Huffman-style codes. And Huffman codes are really cool. I don't know if anybody's ever dealt with Huffman codes. But the cool thing about Huffman codes is that you can encode really frequent things as short bit sequences and really infrequent things as long bit sequences. So, for example, if you look at the Huffman codes that are used for a space, which is a fairly frequent thing in a PSK31 transmission, it's simply a 1. Or the letter E is 111. Those are really short. But a Z, which we don't see very much, is that long sequence of 1s and 0s up there. And we code this such that we can figure out, just from the leading bits, where we're headed. So the first few bits give us a hint as to which codes might follow, or whether the code will actually terminate at that point. And you can actually build a tree. If you know the probabilities, you can build a tree like this that will tell you what's the optimal code set, if you actually know the probability that each particular thing that you're trying to encode will arrive. So if those probabilities are fixed, there's a provably optimal set of Huffman codes that can be used. The problem is we don't really know those probabilities. We only take a guess at them. And so it's not always optimal. There are always messages that are problematic. So we do the best we can. We encode the tree like this, something like this. So you have, like, here's a high probability symbol, A1. That's 0.4 probability. We'll just use a 0 for that, for example. This is not PSK31's code, but it's just an example of an encoding tree. And then you get down here to something very low probability that we make 3 binary bits. So this is a really handy way to encode things, just to make things shorter. CW does this too. You notice the E is very short because it's frequent. And while Huffman hadn't done his proof back when Morse was, or whoever it was that did the original code encoding of Morse code, or the Continental code, they just took a guess, and they said, well, clearly some letters are more frequent than others. A's are fairly frequent, E's are fairly frequent, that sort of thing. And spaces are frequent, and we express spaces in Morse code in a very efficient way, just by extra beats. So there's all sorts of sort of pre-Huffman coding of things built into Morse code. Now on the QPSK, they do even trickier things. And the QPSK uses a form of what's called trellis coding. And in trellis coding, you go through the code set through certain paths that have certain probabilities or certain possibilities. Some paths are even disallowed. And once you choose a code like that, I'm not going to go too much into the particular form of trellis coding that's used in QPSK, but once you have particular valid paths through this state set, you can set up a condition where you have a code coming in. You can put a bunch of decoders in place, maybe 5 different decoders, and you can have all 5 of those decoders running at once. And as you fill up symbols into the decoders, you can figure out which one is closest to something that's valid. And you can actually assign probabilities to each one of these decoders. Once you have those probabilities, you can go to a next step. So you fill up the pipeline with codes, you look at all the probabilities, you take the worst half of them and throw them away. So maybe you have 10 decoders, you throw away 5. Okay, those are the losers. And then you start up a new set of decoders. And you start pushing codes into them. You branch from each of the 5 that are left over. If you have 10 to begin with, you throw away 5. And then you have 5 left, and then you branch for a 1 or a 0 at each one of those. And now you have a set of 10 decoders again. And you carry the probabilities forward from the last one, the scores, essentially, and you keep decoding. And then you get to the next step, and then you throw 5 away again. And eventually you come down to one path that has the best guess, or at least what seems like the best guess, from what information you have. And that actually helps you thread your way through a lot of noise. It's called Viterbi decoding. Viterbi invented it. It's really an interesting system. So with that, we can use these quadrature bases, so we get more bits, and we can decide at each point based on which 2 bits we get, which way we move through the decoder, and then we can choose the best path and actually get rid of some of the noise, or at least get our way through it. So anyway, let's get back to the whole story of how this came to be. If you recall, where we were was that things were just broken. So I stuck all these samples in the receiver, and nothing came out. So I decided to look at some graphs. And once I did that, it became fairly obvious that something was wrong. So this chunk of missing samples, that could have been it. So there was a chunk of missing samples, and look at how ragged that is. See that? That doesn't look right to me. That looks like a lot of high-frequency noise of some sort. So they're even kind of weirdly asymmetric. You can see there's a little more on this side than there is on that side. That's not a good thing. So I went in and I hacked around and I found the gap. And I even found what was causing those ragged samples. And it was Amtech daytime, and so I came up here with nothing on the iPad, just running it inside the simulator on my Mac, and pointed the audio at a signal on the air, and sure enough, I could decode. So there's the first decode right there that this software did. So I wrote this crappy resampler and hacked the whole thing together. I had to recompile every time I wanted to change tuning frequencies. But it worked. I don't know if anybody here was with me that day. It was really fun. I was thrilled. But there was still some lingering stuff. Like every time I tried to decode a signal up at the higher end of the band, it just didn't work. That's always a bad sign. I've learned over the years that when you get some hint that something like that's just a little weird, it's best not to brush it off because it's usually pretty serious. And of course, I had no UI at all, which was kind of painful. So I needed some UI. So what did I do? Well, a long time ago, I was hacking around on the iPhone trying to figure out how to program. So I wrote this fun little program that just takes audio samples and makes a little oscilloscope simulation and VU meter and even has a spectrum waterfall using FFT, a fast Fourier transform. And so I decided to steal some stuff from there and put in a tuning mechanism and cranked on it for another week. And the next thing you know, I had something. And this was also the beginning of my trip to Asia. And so I had a whole 9 hours or 11 hours of flight in that case where I couldn't sleep because I could never sleep on airplanes. And so what do I do when I can't sleep? I write code. So I bashed on this thing a bunch, and then finally, I think this was after I'd gotten there and gotten some more sleep, I actually had some UI. It was pretty crude, but it got the job done. And you could actually see some stuff on a spectrum waterfall. I tore that out of the iPhone app and sent this to myself from Japan so I'd have a record of it. But something wasn't right still. Every time I decoded something, I could see these images appear. And I looked at that and my heart sank because I knew something was just not good enough. Clearly this is a messy thing, and it's going to be hard to fix because it means that the signals are not spectrally pure. And of course, my thought immediately went to the resampling code because that's the part that I did. So I thought, this can't be good. And sure enough, and when I read about how bad moving average samplers are, it was very clear what had gone wrong. But at that time, I thought, I don't want to deal with this. Let's work on the transmitter instead. That's more fun. So I started working on the transmitter. And this is a PSK 31 plot of just the samples. So there's no lines in between the samples. You can see all these samples. They make this very nice pattern up here. And those are actually sine waves. They're just sampled at a very low rate. So I hooked up the audio cue, and I remember just sitting in Japan, just sitting at the table, working on this thing, and I just made a sine wave out of just the sine function, and I stuck it into the audio output cue, and it sounded great. It was this wonderful, pure tone. I thought, aha, this thing's going to work now. And then I wrote another really crummy linear resampler, and I hooked it up to the transmitter, and it just sounded terrible. And I thought, yeah, this is bad. I can't do it this way. I knew what I had in front of me, and I knew that this was probably the same distortion I'd seen in the Fourier transform on the other side. And what I realized was that no cheating was allowed. This had to be done right. And in order to do it right, I had to use industrial strength resampling. And I had, for another project, been looking around for resampling code before, and had never found anything, again, to my liking. It was always tangled up in all sorts of GNU stuff, and copy lefts, and this, that, and the other thing. So, what do you need to do? Write it yourself. And so began the next journey. As I was flying, I discovered this the night before I was flying to Malaysia. So I got on the plane, and I thought, now how am I going to do this? And then I realized that some years ago I had downloaded this great book called the DSP Guide. It's available for free on the internet. And I remember all this signal processing theory. How hard can this be? Famous last words again.
It's only code.
It's only code, right? So I began to write a resampler. And this was the part that was the major pain of the whole thing. So let's talk about resampling and sampling theory in general for just a moment, and then we'll come back to our story. Yes?
This is all the code for sampling rates, all that?
That's right. So the iPad itself can resample, but the simulator doesn't. And when it comes to this kind of stuff, there's this great opportunity staring at you. You can learn about this stuff, and you can get a resampler that you know about, that you know the characteristics of, that you can change the filter frequencies and everything to your liking. So you might think I'm crazy for doing this myself, but boy, did I remember a lot of stuff in doing this. So let's talk about sampling theory. So sampling theory, it sounds really scary, but it's really not that scary. The idea is we have a bunch of time domain signals. So we see this all the time with CD players or whatever. We have these analog signals that in theory, they vary continuously with time. But the way that we deal with them in computers is we can't know all of that information, so we sample them at some periodic rate. So at every so many fractions of a second, we take one sample that represents something called the Dirac delta function, which is like an impulse. It's this impulse that we can actually figure out the original amplitude of. It's supposed to be infinitely thin from a theoretical standpoint, but you can think of it as just a number that we capture at a particular moment in time. Now, there are certain rules that we have to follow. There's this guy named Nyquist who figured out how this sampling theory works. Without going into too many of the details, the really important thing to take away from this is what's called the Nyquist rate. And the Nyquist rate and the proof around this stuff says that if you have a signal, and as long as the highest frequency in that signal is less than or equal to half the sampling rate, that signal can be completely recovered just from those samples. So for example, if you have a 2 kilohertz signal, you know that the signal has nothing faster than 2 kilohertz in it, and you sample it at 4 kilohertz, you can completely recover that signal perfectly. That's what the Nyquist theory says. Okay? So if we manage to actually meet that particular criterion, we can get our signal back. So this is the key part about sampling theory. Now, one of the things that we need to do, starting from getting this audio samples in, is downsample. So some people call this decimation. There's different schools of thought on which term is the appropriate thing for which thing. But let's just talk about trying to get every nth sample. So in this picture here, you can see an example of taking every third sample off of this signal. Okay? Now, when we do this, we really have to obey this Nyquist rate. And down here, it's kind of hard to see. I apologize for that on the screen. But you can see a very fast signal. And if you sample it at just the right rate, which is pretty close to its frequency, you can create this phantom signal. You see this phantom signal? That phantom signal is not really there. And the reason that we saw it was because we violated this Nyquist rate. We sampled it faster than half the frequency of this signal here. And so we get these false signals. We call these false signals aliasing. And when I drew these little circles on top of the sampling waveform here, I realized it was a perfect demo of aliasing, because if you move them just one sample over, look at what you lose. You've completely lost that. This is just a flat line now. So you can see that's sort of aliasing in another direction. This is cool, turned on for good. That's aliasing in the other direction where we lose detail. Okay, so there's phantom signals created where we can lose detail. So in order to actually do this correctly, we have to put a filter on that ensures that we have nothing faster than half the sample rate. And then we can, and where I say half the sample rate is the lower sampling rate we want. We have a high sampling rate, we want to make it lower. We get a filter that cuts off anything greater than half of that new sampling rate we want. And then we can just choose every nth one. And that's how we achieve decimation. Okay? Now the moving average that I used originally, it mostly works, but it creates all of these high frequency harmonics. Okay, so that's why I was able to receive. It's just not very good. And the further you push it towards the edge of the passband, the worse it gets. Thus, the behavior I saw. Now, upsampling is a similar sort of thing, but it's a little more tricky. Okay, so there's a couple of different ways to upsample, and the one that's most sort of theoretically pure, and actually, as it turns out, quite efficient to implement, is to take a filter that is at the Nyquist rate for the new frequency. So we have a new high frequency we want to sample that up here. We put our filter at half of that, and then we just pass impulses through the filter, which are the low samples. You know, every nth sample through the filter, we push it through. And then what pops out is beautiful waveforms. Okay, so if you look at this signal here, this is at a high rate. Okay, so, or I'm sorry, this is at a very low rate. You can see that the samples, especially up here, there's only a couple of samples per waveform. But when you push it through an interpolator, you get these beautiful sine waves. And that's because these sine waves are implicit in the samples because we have made sure that the Nyquist rate is met. All of that is theoretically implicit. So if we take this filter at the new rate, and we just push every nth sample through it, we can get out the original signal at that higher rate, complete with all those beautiful sort of interpolated sine waves there. So it's really quite dramatic when you see it the first time.
Effectively, what you're doing is you're interpolating half the samples and you're calculating 20.
Yeah, but it's not a matter of, you can't simply just draw a line, and you can't just draw a curve, or even a polynomial curve. All of those are wrong. It has to be made of sinusoids. And that's why this filter method is really pure, because you're just putting an impulse into the filter. The filter has this thing called an impulse response. That impulse response will be sine waves near the cutoff frequency of the filter. It's like pinging and watching it resonate. Okay? Now, a key element in all of this is building a low-pass filter. We're all familiar with this as hams. We use low-pass filters all the time. And this is the key element that we need to have in order to enforce this Nyquist rate. And just to refresh your memory about filters, they have a cutoff frequency, and below the cutoff frequency in a low-pass filter, it passes stuff, and above the cutoff frequency, it begins to not pass it. Okay, and that's called the stop band. And they're not perfect usually, especially analog filters. They have these sort of slow roll-offs. We usually make them out of resistors and capacitors, many other more sophisticated designs, but that's the basic thing. And what we need to do is build a digital version. And this is the scary part. Don't be scared too much. But I need to tell you just a little bit about it so you'll see why we have those funky waveforms on there. We use a technique called convolution. Convolution is a mathematical operation. That's the convolution integral that's actually supposed to be from minus infinity to plus infinity, but we couldn't find an easy way to express that in that font. But anyway, the point is that we use this operation to do digital signal processing all the time because it has this interesting property that if you take a signal and you take its Fourier transform, it turns in Fourier space into multiplication. Just simple multiplication. And this allows us to take, say, the frequency here and multiply it by a step function. Okay? So this step is like our low-pass filter. Here's the stuff we pass, here's the stuff we don't. This is our cutoff frequency right here, and we want to multiply that by the frequency spectrum inherent in the signaling that we're interested in. So what we can do in order to get that is to take this waveform, do an inverse Fourier transform on it, which turns out to be this thing. When we do the inverse Fourier transform. And then we can do the convolution operation. Now, all this scary looking calculus up here turns into multiplication and addition for samples. So it's quite cheap to do. So what we can do is take this, do the inverse Fourier transform, which we know already. It happens to be this thing called sinc, which I talked about earlier, which is sine x over x. So once we have sine x over x, we can generate this interesting looking waveform and go back into the time domain and do this convolution operation. And we get, magically out of that, just by the pure mathematics, a low-pass filter. And so we do it just like this, same waveforms, only we get the samples. You see these little dots here. Those are just the samples. And the waveform I showed you earlier was actually my own convolution filter. It was its own little convolution kernel that it had generated, and then you get just this multiplication. It's reasonably simple, as it turns out. Now, there's one problem, though. You have this great sine x over x, it looks like that, but there's a problem in that sine x over x goes on forever. It never goes to 0. And, of course, we're talking about a finite thing. We're going to finish the calculation at some point. So what do? Well, we have to cut it off. But you can't just sort of chop it off here, because that'll create frequencies that are not there in the original. And this is where we get into kind of hand-wavy land. So not based on theory, but based on experimentation, people have found what's called windowing functions. And these windowing functions are sort of laid on top, like this, and multiplied by this, to create a flat, sort of nicely ending sine x over x. There's a couple of different windows you can use. I mentioned the Hanning window before, also called the raised cosine window. The one I chose to use is the Blackman window. And these are named after the people who experimented with them and just happened to come up with these magic equations that happen to work well, not because it's theoretically predicted. Sorry?
It's kind of a slime fit.
I'm sorry?
Looks like a slime fit to some degree.
It's trigonometrically generated. It's cosines and sines. But you end up with no sharp transitions, and this is my filter kernel. You notice that it stops oscillating sort of out here somewhere, and it stops oscillating very slowly. Okay, so it makes you this nice filter kernel. And once you have that, all you have to do, and it sounds simple, all you have to do is do the convolution. But it turns out that there's some tricks you can do, because we're doing things called upsampling and downsampling. So we end up with a lot of zeros, because either we're forcing extra zeros into the filter, or there's a bunch of things that come out of the filter we don't care about. And every calculation that has a multiply and a 0 in it is 0. So we can skip those. It's pretty handy. So if you look, we use a very fast way to do it is what's called polyphase filtering. This is where we do several samples all at the same time. This can be very efficient on certain vector processors. But in this case, we're not taking advantage of it using vector processors or parallel processors or anything like that. We're just noticing all these zeros. See them all? They're all zeros, all in between the samples. And the samples kind of march through in this direction, down through this matrix. Okay? And if you look at, these are the filter kernel values. These are the samples coming in. And the samples come in through these rows. And these are the results here. And these result in these very simple equations right here. Just some adds and some multiplies. Not much to it. With a lot of zeros in them, so they're pretty short. And if you take these things and you order them in a different way, you can get them so that they come out 0, 4, 8, 1, 5, 9, 2, 6, 10, 3, 7, 11. so that you can just increment a pointer and just go bam, 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 bam through these things very quickly. Okay, so this gives us a really optimal way to do interpolation. So we plug the filter kernel in here, and we just march these samples through the polyphase interpolator, and bam, out come those beautiful sine waves. Downsampling is a little different, but we get certain advantages again. It's just a little more computation, because we actually have to run the entire filter kernel through every sample. But we don't have to do every sample that we want, because we're going to skip every end. These are 4-to-1 resamplings, by the way. They're illustrated in the diagram. So here we have sample 0, sample 3, sample 7, sample 11. We skip samples 1, 2, 1 and 2, because we don't need them. Okay? So we go through, and we have this big, long addition and multiplication. But computers are pretty good at doing this stuff. And if we pipeline it really nicely, we can get it to go, unroll all the loops pretty fast. But this allows us to, again, enforce the Nyquist frequencies and choose our samples and skip everything we don't need. So now that we have sort of the kernel, now we have to figure out how to get from one frequency to the other. And one of the things you may have noticed as we were going along here is that since these are sort of square matrices, we only get integer changes. So we can upsample by a factor of 2, 3, 4, 5, 6, 7. But if we want 2.5, this doesn't give us a clear way to do it. So what we can do is do rational resampling. So a rational number is any number that can be made up of a ratio of 2 integers. And with something like that, we can combine operations between interpolating and decimating to get any resampling ratio that we want that's expressible as a rational number, at least in theory. Okay, so for example, one of the things that pro audio people always use 48K samples per second or some multiple of that. If you want to get from 48K samples per second to 8,000 samples per second, you just, it's 48 over 8 or 6. Well, that's easy. Upsample 6, downsample 6, piece of cake. Problem is though, a lot of audio systems based on CDs use 44,100, which is not very friendly. So you divide that by 8, you get 5.5125. And you can see where my little linear trick just really failed because it had to do skip things to get the samples right. So we're going to have to do more tricks. And it's even worse because there's no common factors between these two numbers other than lopping the 2 zeros off the end. You get 7 times 7 times 3 times 3 and 5 times 2 times 2 times 2, which is not a friendly set of numbers at all. So unfortunately, we have to do every step. Now, the best way to do this from a theoretical perspective is to do all the upsampling and then do all the downsampling. And that's just not practical in many of these cases because the amount of memory you need to do all this upsampling. I'd have to upsample 44,100 samples per second by 441 and then bring it down. It's just not going to happen. So, or 8,000 by 441 and then down by 80. So what you have to do is find sort of the best compromise of going sort of up, down, and that's experimentally determined. So that's a little bit of sampling theory, and with that, we'll return to the story. You remember I was at this place where I needed a better resampler, and so I spent an entire plane flight to Malaysia writing these resampling kernels. And what I ended up with was a very nice set of stackable resamplers. This is an Objective-C, but you can just sort of plug in the up ratios are plus and the downs are minus, and you just stack them all up at initialization time. It calculates all the kernels, and you have now a stack of resamplers that will either go up or down depending on which way you put the ratios, which is a kind of handy little tool, because when it came time to figure out whether I was going to go up and down, I just had to swap these things around until they made sense, and the numbers didn't overflow or underflow. So you can see what I ended up with here. I go up by 7, down by 5, up by 7, down by 4, up by 9, down by 4, and then flip that upside down to go the other way. And that turned out to be reasonable. I'm not saying it's the best, but it works fine. There was also some playing I had to do with amplification into the filters. Especially when you're interpolating, you're putting these impulses in, at a much lower frequency, so the signal energy is really low, and you have to adjust the signal energy up appropriately to recover enough energy so the amplitudes are kind of where you hope they would be. So it's a lot of playing around. But I finally got this nice little stackable set of resamplers to go, which was a very, very nice from programming standpoint to have for experimentation. And then it came time to optimize, and it just, right out of the box, was way too slow to work. So I had to play around quite a bit. And I used all the old tricks I know from my embedded programming days, which was to just unroll a lot of loops, do some things that were optimal for some processors or optimal in a different way for other processors. Like sometimes it's more optimal to just increment and decrement the pointer. Some CPUs do that very efficiently. Others like offsets from their pointers as fixed static numbers. And it turns out that iPad's ARM processor likes this flavor very nicely. And there were other little tricks I did to try and keep the memory traffic low. You try to take all the invariants out of the loops. Sometimes the compilers do a decent job of this, but they miss stuff. So it's better to coerce the compiler into doing the right thing by making sure you take all your own pre-computed invariants and pulling them out of the loop, sticking things in variables, and then it'll usually do a good job of filling the registers. It's the register allocation algorithms are very good these days. And I got it so good that no matter what I did to it, I couldn't get it any faster. And that told me I was right up against the memory bandwidth, at least for that processor. There's probably more optimization I could do, but this was, you know, this kind of stuff was good enough here. One of the things I haven't done yet that I will do is change everything from double wide floating point to single wide floating point. That will improve things at the cost of accuracy, but I haven't done that yet. But one really sticky problem I call residue, which is, I guess, appropriately sticky. And that is that sometimes you don't get enough samples to complete one operation. So let's say you're downsampling. You need at least 10 samples to create one sample, but you've only got 6. What do you do? Well, you kind of have to pause that downsample and hold the state of the world and wait for the next samples to come in later, because you get them in chunks. So when the audio hardware is sampling audio that's coming in, it comes in discrete chunks that are so big. And sometimes you just don't have more samples, and you have to wait a half a second for some more. And so you have to save stuff around the edges. And if you do it judiciously, you can actually set it up so all the stackable resamplers have their own stored state, and they all track perfectly. So that when you pump samples into one side of this giant stack, all the proper residue gets saved at each stage, and they just chunk right through, and all the right stuff comes out. Now, as you can imagine, it's really easy to screw this up. And I did many times. I by no means am perfect at this stuff. So it ran the gamut from really subtle stuff to really blatant stuff. You saw the big chunk of missing samples before, that was pretty blatant. But this one's slightly more subtle. You can see this just kind of looks ragged here. That's a sign something's wrong. And you know, oftentimes I'm trying to do this optimization where I'm doing a lot of pointer calculations. Sometimes you just blow it. You know, you don't multiply by the right thing, you don't realize something needs to be added. Sometimes it works perfectly in some cases and then just makes a little subtle mistake later on. And the real problem is the errors can be filtered. So by the time you see them, they've gone through several other filter stages, and now they look really weird. So one thing that I found was really effective was listening. I would just listen to the output and say, something's not right. This doesn't sound right. And then I go back and know that I wasn't done. And so I'll show you a few of the fun things. Here's where you lost just a portion of a cycle. And again, GNU plot saved me, because I would just spit out usually 2 audio buffers worth of samples, stick them in GNU plot, and take a look, and sure enough, something would be wrong. Here's another one where it didn't really lose it, but it kind of lost sync, and it just jammed a few together. And so you got a sharp transition there. This next one is really subtle. See what's wrong? Anybody see what's wrong? Guesses? So look at the envelope. See how it goes up and down again? Shouldn't be doing that in that particular spot. I know it's a little trick question, because it's hard to know what's going on in that spot, but that amplitude change is wrong. And I could tell sometimes too I would often transmit with this thing, for example, and then listen with one of the other programs and see errors. So it would kind of go along, and every once in a while there'd be a wrong character. And I was transmitting from the speaker on the Mac back to the microphone. That should work just fine. And when things are right, indeed it does work just fine. But with these little errors, you never know. Here's another one. You can see that it just lost a bunch of samples in the middle here. And so if you looked at this cycle, it looked perfect. I think this was a transmit waveform. And you look here, it looked really bad. And there were different errors in transmitting and receiving too. So I would get one right, and look at the other, and see what I did wrong. Here's another fairly obvious one that you had to catch the right cycle. And so sometimes I would multiply the number of samples by the upsample and downsample ratios, and then I'd search around looking for the cycle that would be wrong. Here's one that at this scale filtered. So it's really tricky. Here's another one that's sort of like that, only that's got some other really weird variant here. This one is particularly interesting because this error clearly occurred several filters ago and just got really nicely smooth. So once I finally got the resampling to go, there was a lot more UI work to do, and it just took a lot of slogging through it, experimenting with this and that until I was happy with it. I'm still experimenting, playing around with things. I needed to get the keyboard to work so I could input text. I needed to have tuning sliders so I could actually tune the thing. I needed to be able to turn the transmitter on and off. I have macros. And all of this stuff I wanted so that I could actually make a QSO. I don't want to get on the air with this thing and then go, oh my god, I can't type the thing I need to do right now because I'm trying to talk to this person. I really wanted some minimal set of control before I could move on. And one of the things that I thought would be cool and easy to implement is call sign parsing. So it turns out, call signs are pretty easy to parse. You can make a reasonable guess that something's a call sign by just writing the right regular expression, if you know regular expressions. And so I just wrote a regular expression that tends to pull call signs out. And I figured only humans really know if they're really call signs or not. So I just present them to you and you get to choose. And so once I'd gotten enough UI to go, this actually was a long slog through most of my Christmas break. I was pounding on this thing. It was time to just test. And I tested everything. And I really didn't want to get on the air until I knew this thing was going to work, because I wanted to come here to Amateur Radio Technology Day and have it hopefully be a glorious success or a terrible failure. But at least I wanted to put the work in ahead of time with the highest, so I could get the highest probability of success. So I grabbed all the different programs that I had lying around that did PSK31, and I transmitted to them, and I received to them, and I recorded signals off of WebSDR. .org. I don't know if you've seen that. That's a whole bunch of SDR receivers on the web that run in some kind of Java thing that's very sluggish but works. And I think I may have some audio here. Yeah, you can hear what it sounds like. I just went on and grabbed some signals from Hungary or something. And I have a bunch of audio files full of this stuff, and I just point the thing at it and I start listening for signals from receiving, making sure I can get stuff. This turned out to be a particularly hard set of signals to decode, so it was a really good test for the receiver. It's pretty easy to make a receiver that just works, but to make it work in this kind of a noisy and sort of signal competitive environment is hard. You really know, when you can decode this stuff, you really know it works. I also transmitted transceiver to transceiver with a dummy load, so I stuck a dummy load on the K2, and I listened on the 756, and I was able to decode, and I did this about a week before January Amateur Radio Technology Day, just to make sure it was going to work. And just as a little side note here, I discovered, and I should have known this all along, but I didn't think about it before, that BPSK is actually symmetric in Fourier space. And what that means is that it doesn't matter what sideband you transmit or receive on, just as long as you have the frequencies aligned properly, it will work. And I discovered this by accidentally doing it on the wrong sideband. And it was working, and oh no, this is what it was. I was listening to some guy in white, and I was on 40 meters, so I had set the lower sideband. I'm just holding the iPad up to the receiver, and I'm watching this QSO, and then it occurs to me, wait a minute, why is this working? And then I thought about it for a minute, and it was obvious. The sidebands are perfectly symmetric. It doesn't really matter. QPSK, not so. QPSK is not symmetric in Fourier space, but this is. So that was kind of a fun discovery. And the last step of all of this was to get the hardware together. So what do? You have to get audio in and out of this thing. And I thought, well, it has analog input and output. I don't need much in the way of bandwidth, and I don't need much in the way of just general quality. I can just throw something together. So I looked around, and you know, there's this funny jack on here that has a bunch of rings on it. And I found that I had an iPod AV cable just sort of sitting around that belonged to something else, maybe a TV monitor or something. And I got my standard rig interface. I don't know if you guys have seen this before. I use this up here fairly often, which is really simple. It's just a pair of audio isolation transformers. You can get them at Rad Shack. If you're lucky, if you find some, just buy them up because they're going to go away at some point. A couple of pots and the right wires to go in and out of the rig. And in my case, there's a microphone. The only complicated part is somewhere buried in here is a microphone cable for Kenwood. There it is. Okay, and that just plugs into the K2. The K2 has its own AGC, so you know levels don't matter that much. You also have to trick the iPad into thinking it has a microphone, which turns out to be pretty easy to do. I just read up on the internet about it. You put a 1K ohm resistor on it, and eventually it says, oh, you must have a microphone here. So I padded the signal down about 30 dB, which means about like 33K voltage divider with 1K on the bottom, and hooked it up, and I could receive. Easy peasy. And then for transmitting, who needs push to talk? You don't need any push to talk. All you need is a box for PSK. I've been using that for years. So no extra control signals needed. Just turn on box on your radio, and when the thing starts, you know, put it on fairly slow, like a second response. And when the PSK31 program wakes up and starts making noise, the thing will start transmitting, and everything is hunky-dory. Usually there's enough synchronization signals. Actually, a PSK carrier starts with a bunch of zeros, because zeros mean phase transitions, so you can actually get the clock lined up. So you send a whole bunch of zeros. And within a second, that's plenty fun. But if you're contemplating running PSK, don't worry about this PTT stuff. Just use a box, it works great. And so here's a close-up of the, this is my stupid little board that I've been using for years. $10, can't beat the price. And this is this little RCA connector that I stuffed with the voltage divider, which is uninsulated, but that was just to show everybody. Yes?
I would just mention Fry's has the right iPad cable for about $3.70 with the bare ends.
Oh, but does it have the pad in it?
With the right combination of rings.
Does it have the voltage divider inside?
No.
Okay.
You have to have the 700 plus ohms.
Okay, so what I happened to have lying around was the right combination thing, but it was designed for video for a standard iPod. Okay, and I just figured out which connectors went to which rings, and it was fine. And that's why I put these RCA connectors on here, was because that's what meant that particular wire. I have it all here if you want to see it. But that was the kind of easy part. And once I had the hardware together, this was about 2 days before the big day, and then came the big day itself. And the first I saved, I picked day number 73, which was somehow appropriate, for the big day. And this was on the 29th of January, and I did my usual trick of arriving at the crack of noon, or getting up at the crack of noon, and arriving at 2 in the afternoon. And I got the whole station together, which turned out to be almost entirely something I had built. The only thing I didn't build was the battery pack. I built the rig, I built the antenna, I built the iPad interface, I built the software, and even the Arizona Scorpion key you see up there, right there, I built that too, from just brass pieces. So that was fun. And so we got it on the air, and
Is that PSK31?
yes.
Don't mind the camera.
Gerald said,
To talk to one of my friends now.
You do talk to a friend now.
Well, yeah. I don't know her as well.
Oh,
Okay,
was that great?
Yeah.
Okay, cool.
When you're begging for
Yeah.
discounts, it
Yeah, yeah, yeah.
pays to.
I'm thinking of running.
That's not bad.
That's not bad. Tell them what you're running.
Copy. Well, I'm gonna try doing push buttons.
Yeah.
Everybody stay away from things that doesn't break. Okay, don't touch anything.
I love the debug part.
Well, there's ants on the table, does that count?
There's ants on the table.
Yeah.
You need to give it to us.
Ants on the table? You have to have ants on the table.
16 ants.
Well, there's only two. At least that I can see. There's a dead one.
So what are you running this on?
iPad.
And your radio is
K2.
K2. Oh, it's quite a
So coming out right there. So it looks like the whole station.
noise.
It was like 300 total. That's what makes it work. Yeah.
It's the ant hours.
That's not a bug, it's a feature.
Yes.
So that was basically it. There's more video. It's on YouTube if you want to look it up. Just look for iPad K6WX. Thanks to Ricky, K6WX for who's videotaping today as well, for taking that video and putting it up on YouTube. And results? Well, we worked 6 stations, including Asiatic and European Russia, Argentina, Japan, and a couple stations in Texas, and I have one very nice QSL card. That stuff at the top there, you can see a hint that I actually have logging built in now, so it will log. And in fact, it will even send you ADIF formatted files in an email, so you can stick them in your larger log. So that's some new stuff. So looking at all this, you wonder what's next. Well, there's lots of things to do. It's a never-ending task. You can see I did some fun stuff with changing the color scheme for the pulse colors in the FFT. There's a lot of other things I wanted to do. The logging was a big thing because I was paper logging there. But now I actually have a thing where you can just tie it to a button and log, and then send yourself a log. And you can also edit all the log entries. I want to put some QRZ integration in, although their database is a pain to, you have to actually pay the money to use it, which is a pain. I don't know what to do about that. I really want to rewrite PSK modem myself. I don't like the way it's organized. I would do it differently. It uses a few tricks that are a little marginal in my humble opinion. I think it would be a really fun thing to do just so I learn more about it. And new modes. I'd like to do other modes. People are interested. You have a question?
Did you have any trouble with iOS 4?
No?
No, because I have some audio things that, when I wasn't multitasking, the audio went into those apps.
Oh, really? They may have been old apps that were not.
It really goes on in the background, the audio.
Oh, that's interesting. That sounds like a bug.
Started just.
Interesting. I haven't had that particular problem. There might have been apps that were not upgraded at the time. All of this stuff was written under the latest, greatest development environment for iOS 4. Whatever is current, which I believe is 4.2 something. And so it seems just work. I squashed a bunch of memory leaks recently and took care of a couple of cases where memory warnings were giving me bad things. But anyway, new modes. One of the things that I came up with that I really want to try is I talked a little bit before about trellis coding. There's something about Morse code that's sort of trellis encoded slightly. I want to do a Viterbi style decoder for Morse code. I think that would be really interesting. I alluded earlier to a couple of, there's a different modulation scheme that keeps the amplitude constant. It also does some phased encoding. I want to try something like that maybe and lock one of the sidebands off. And maybe that will be narrow and efficient. And combine that with some convolution coding or something like that. It's all as time permits, but I'm certainly open to suggestions. Some people are really interested in JT65A, whisper type stuff. Maybe that history. I can't hear you.
MT63.
Yeah, could do that. Could do that. That's the multi-frequency FSK style thing with 16 frequencies instead. So anything that's signal processing oriented can be done. There's a sort of a class hierarchy there, so I can just swap out a different signal processing class, and in theory it'll work. We'll see. Yes, Peter.
We want to face this way, the radar display.
Yeah, that's something I might do. One of the things Lee, W85ZNU is really interested in doing sort of multi-decoding with QRZ integration. So I want to add another thing in so you can just look at 20 decoders and then add in QRZ info and have it scroll by. Just throw people's info into stuff that might be logged if you choose to talk to them. Push the button, you'll switch back to the more familiar display. So, one thing I'll say here is that I haven't done anything outlandish at all with how you interact with this thing. It's pretty standard ham-style PSK, what you're used to kind of thing, except that you do it with your finger instead of a mouse. But I want to experiment with some new stuff. That's the next stage. Daryl, yes?
Thought about text-to-speech?
That's a lot of work. A couple of people have asked me about that. I don't know how to integrate, like, say, Dragon. I don't know if they have a library that one can use.
I wouldn't do Dragon. This Apple.
There's text-to-speech on the iPad.
Yeah.
I'm sorry? I'm having trouble hearing you. I'm sorry.
Isn't there text-to-speech already on the map? Already on the platform?
I think there are certain things you can train it to listen to, but if you want to do generalized text-to-speech. Oh, text-to-speech. Yeah, that may be doable easily. The other way around is.
So I wouldn't do it the other way around. Actually, most of us who are visual effects would just type it. Just sit back out.
All right.
Have
Well,
the text on. I mean, I forget the speech.
yeah, that may be quite doable. The only potential issue is, of course, badly spelled words because of errors.
At least we can tell.
Hang on, I'm going to take lots of questions in a minute. Let me get through the last little bit here, and then we'll take all the questions. But anyway, if you have suggestions for things to play with, I'm pretty open to coding stuff as long as it's like not a huge time sink, because this is all just for fun. But in conclusion, the thing I really learned out about this, about myself anyway, is that frustration is the mother of invention. I'm so obsessive. Okay, so when I get frustrated is when I go into these things, and I'm really obsessive about them once I grab onto it and say, I can't let it go for months at a clip. So I'm really having fun with that. And digital signal processing, I'd forgotten how fun it was. I took this wonderful course at MIT 6015, for those who were there, which is no longer taught, sadly. It's now 6003. But anyway, it was a great course on all of this stuff, all the way up through Laplace and Z transforms and all that other fun stuff. But it was really good to revisit that world. I haven't worked there in a while. I used to do research on image codecs when I was at Sun. So it was fun kind of being back in space. There's no real shortcuts, of course. I got burned by that. I knew that in my heart, and I knew I was trying to get away with something, and of course it failed. But of course, I learned something in the process. The iPad is a wonderful platform for doing DSP on ham radio. It's plenty fast enough to do all sorts of fun stuff, and it's got this nice big screen. I know some of you are going to ask about iPhone. The screen's really small. It's hard to do good stuff for ham radio in this particular way with that small screen, but that's the beauty of iPad. And homebrew, this is what amateur radio is. So I'm hoping that this will inspire some of you, because to me, the real fun of ham radio is building the stuff that we use, building the antennas, which you all know I love to do, building the radios, and now building the software. It's just a hoot. So if you want to know more about this, you want to know more about developing for iPad, you can go to developer.apple.com. The DSP guide, dspguide.com, that's Stephen Smith. It's a great sort of practical, without a lot of theory and math, book on digital signal processing. So it'll take you through some of the math, and it'll just say, okay, here's how you implement it. And it has pseudocode and everything. Very nice book for that kind of stuff. DSP Guru is kind of a much more summary bit of information. They have some, I think, copylifted resamplers and stuff up there. I don't look at any of them because I wanted to write my own stuff. And if you want to go visit the MIT stuff, that might be a derivative of what I learned, but I don't know. I didn't really look at it in much detail. You can go to the 6003 course page on opencourseware.mit.edu. That's ocw.mit.edu. Now I'll take any questions. Yes?
Actually, a couple. So when we were first looking into these to do the normal digital mode here myself, we're using FLDigi video, but what do you think about the FLDigi mode?
So I can't say that I looked at the signal processing part of the FLDigi modem.
He's asking-
Okay, I'm sorry. The question was, what did I think of the FLDigi modems? So I can't say that I looked at the signal processing stuff in that much detail. I was so turned off by the intertwined mess that it was between all the GNU, wobulator, define, snort, configuration, this, that, and the other thing, and UI code wrapped up in this modem that I tried to compile. I worked for half a day on it, and I just said, no, this is not right. I'm not doing this. I'll write my own first. So it, these guys put a lot of work into it, obviously. I don't want to denigrate that, but it's not the way I would have organized it.
So the other question I had, so you mentioned the modem that you did pick with the C++, but the iPad is Objective-C. Did you port all of the work, or is Objective-C so that you run C++?
So the question was, the modem was in C++, but the iPad likes Objective-C. What did I do? So there's Objective-C++, and there's just C++. They all work on iPad and iPhone. The compiler will compile all of them. Objective-C++ can really warp your mind, but it is quite doable. I've done it before many times. In this case, what did I do? There's like 1 or 2 files that bridge that are in Objective-C++, where I will instantiate the C++ class. There's some Objective-C wrappers around it, and then that passes off to the Objective-C world where I do all of the UI. So it's a little bit mind-bending.
Okay, my last question was, you mentioned that the emulator required the downsampling and upsampling, but the hardware itself would do 44 kilohertz. So when your application is running, do you use anything for resamplers at all?
So the question was, the simulator only does 44 watt apparently, at least I couldn't get it to go at any other rate, but the hardware in the iPad does resample. Did I use that? No. Not because I discovered that it was inadequate to the task, but I wrote this resampler, I wanted to use it, so I did. And it's plenty fast. So it occupies about 20% of the CPU. Yes.
Are we going to see this in the App Store?
Ah, the big question, we're going to see this. I don't know. Time will tell. I have to seek permission. I'm an Apple employee, so we don't get to naturally participate in the App Store experience. So I have to seek special permission to do that. Yes, Michael.
What about code?
I'm sorry.
Code,
The code. Oh, this is the open source question.
publish.
I'm not a big fan of open source. I work really hard on this. I don't just give away my labor for free. You're welcome to look at it. I'm not going to publish it on the internet. Yes?
Can you go back to the slide before this and hit the references? Is that hard to do? I just want to mention that one at the bottom, the OCWMIT review. I went over there and there's I guess the term I would use would be mass quantity of courses that MIT offers there for, I guess, online study and involvement. And the only thing that I thought was interesting about that was there were several spots on the various pages where they said donations. Well, we didn't say what the donation was, but they said donations. So I really don't know what the donation amount is, the one we get for a course, but there is a large quantity of courses available at that website, so I suggest people go over there and check it out. So.
Yeah, the OCW is a great resource. The quality varies. It goes anywhere from some professor just throwing his course notes and problem sets up there to complete problem sets, answers, videos, references to the text, etc. And in particular, if you happen to go there, the best thing is download, if you like physics, download the 801 and 802 lectures for freshman physics, that's first and second term. And you'll hear Walter Lewin, who is just wonderful, and helped get my son through a number of physics problems. But if you, the most fun class at MIT is freshman physics. It is a hoot. It is really a hoot. I think you'd enjoy it if you like physics. So yeah, great resource. Any other questions? Yes?
You mentioned your stackable resampler.
Mm-hmm.
How deep can you stack that?
Until you run out of memory and CPU. So yeah, that deep.
Whichever came first.
Yeah, so it's just an array of objects, and you will it pre-computes all the kernels at init time, and so you just push the samples through, and they'll just go until you can't compute them.
That was sort of my question, when, at what
So-
point do you run out of memories?
Yeah, so I don't know the exact answer to that, but I will tell you that I'm using about 20% of the CPU right now to do 44.1 downsampling to 8 kilosample per second PSK demodulating. So you can draw your own conclusions from that.
And what are the buffer, you do the buffer, what how much memory do you use?
Not a whole lot. So I use the audio system in iOS and in Mac is based on a set of buffers in a ring. So it's not a ring buffer per se. It's a bunch of buffers you reallocate. I use 3. Seems adequate. And every buffer on receive, I actually spin them off on another thread. This is actually highly multi-threaded. So I spin all of the receive stuff off on another thread. So I pull it off the audio cue, I stick it on another thread, the other thread crunches through it, so the receiver can actually get behind. The transmitter cannot, obviously. I can, I preload a bunch, but then it has to be within the preload. So the RAID can't get too behind. Yes?
One of the other maybe is a future feature, does the iPad have enough horsepower and resources to do like a PSK browser where you put multiple PSKs and you can pick what that person's doing CQ or this or that?
So the question is, can I do a multiple browser? I think so. I haven't tried it yet. That's actually maybe the next thing I'll work on. I wanted to do logging first. But I haven't pushed the receiver. Now, the good news in that domain is that you're always doing the work at the low sample rate. So you have a little more leisure time. So I'm hoping I can get 10, 12, 15 if I'm lucky. We'll see. Right now I'm doing 2. That's doing okay.
So you work with multiple, right?
Oh yeah. It's just, an array of decoders in the class. So I thought they turned your programming so nice. I'm glad somebody went to the trouble of making that stuff work. Yes?
The FIR filters are conceptually simpler, but IIR filters are more efficient. Why didn't you consider IIR filters?
So the question was, why did I use finite infinite response filters instead of infinite impulse response filters? So IIRs are a little harder to design. When it comes to the interpolation, the FIR method is so fast that it's hard to not give it up. Now, IIRs can be shorter, but with that polyphase model and all the things that disappear, it's just not worth it most of the time. Most people don't use IIR filters for the interpolation because it's so efficient to do it with FIRs. Now, on the downsampling, sure, I could have, but this was so easy. I just, generate my little sync at the right intervals, multiply the window on top, done. No states to worry about. And then just multiply. It's really easy to unroll those loops. So, not particularly good reason, except